Okay, Assalamualaikum and a very good morning. Okay, let's look at the antenna equivalent area, or the effective area, also known as aperture of the antenna, in which the area when multiplied by the incident power density give the power delivered to the load. Okay, so this is the incident or the incoming wave. So this is the aperture. The effective area when multiplied by the incident power gives the total power transferred or delivered to the load. Okay, the antenna equivalent area or the effective area defined as the ratio of the available power at the terminals of the receiving antenna to the power flux density of a plane wave incident on the antenna from that direction. Okay, from this direction, the incident power multiplied by the effective area results in the total power at the receiving terminals. Alright, so mathematically, the total power PT delivered to the load, okay, is given as Wi multiplied by AE. Wi is the power density of the incident wave, the incoming wave, multiplied by the effective area in meters squared. So the effective area or the aperture can be calculated by dividing the total power radiated to the load divided by the incident power density. Alright, and the an antenna can be represented as equivalent circuit as shown in this figure. So RL is the load resistant, RR is the radiation resistance, and then RT is the total resistance. Okay, and this equation, this effective area equation, can be further modified considering the equivalent circuit, and the equation be expanded to this, considering all the resistance in the equivalent circuit, and under maximum power transfer condition or in conjugate matching condition, so the maximum effective area can be calculated by this equation. Okay, so this maximum effective area can also be simplified to lambda, the wavelength squared, divided by 4 pi d naught, the maximum directivity, considered there's no loss. Okay, theoretically, under conjugate matching condition or under maximum power transfer condition, only half of the captured power or collected power by the antenna or by the effective area will be delivered to the load. So after the aperture area received the incident wave, alright, so only 50% of the total power will be successfully transferred to the load, while another half will be scattered and dissipated as heat. So in order to consider or to take into account the total power scattered power and dissipated power, so we need to know or to calculate the effective area for scattering and also loss and capture. Alright, so the scattering area represented by AS is basically the area when multiplied by the incident power density will produce the total power scattered. Okay, so considering the resistance, radiation resistance, the load resistance, and etc. And loss area is the area, okay, when multiplied by the incident power density will produce the total power dissipated as heat through the RL. Okay, while the capture area is the area when multiplied by the incident power density will result in the total power collected or captured by the antenna. And these are the equations to represent or to calculate the effective area based on the different conditions: scattering, loss, and capture. And the capture area, the AC, is actually equal to the effective area AE plus the scattering area AS plus the loss area AL. And another important parameter to take note is the aperture efficiency, okay, which is basically the ratio between the maximum effective area divided by the physical area of the antenna. Okay, so this is the aperture efficiency, in which for aperture antenna, the aperture efficiency should be less than 1, while for wire antennas, the aperture efficiency should be larger than 1. Next, we are going to discuss the relationship between the maximum directivity and maximum effective area. So we are going to consider the transmission setup, which consists of two antennas. The first one is the transmitter, and the second antenna acts as the receiver. Okay, if antenna 1, the transmitter, is isotropic, okay, its radiated power density W0, not representing the isotropic condition, at distance r from the receiver can be calculated by using W0 equal to PT, the total radiated power, right? PT, total radiated power, divided by 4 pi r squared. Okay, and the actual density of the antenna or the transmitter, antenna 1, WT, T is representing the transmitter, equal to W0, the power density of isotropic condition, multiplied by DT, the directivity of the transmitter, equal to PT, the radiated power, multiplied by the directivity of the transmitter or the antenna 1, divided by 4 pi r squared. And the total collected power or the captured power by the receiver or the receiving antenna, and then it will transfer to the load, is given by PR, okay, the received power, and the power will be transferred to the load is given by WTER. WT is the power density from the transmitter, that's why it is T, okay. The power density from the transmitter that receive at the receiver multiplied by the effective area of the receiving antenna, and the equation can be rearranged into dt multiplied by AR, the directivity of the transmitter multiplied by the receiver, effective area of the receiver, is equivalent to the ratio of the received power divided by the transmitted power multiplied by 4 pi r squared. Okay, the other way around, if now antenna 2, okay, now this antenna 2 is used as a transmitter, and antenna 1 is now act as a receiver. So but the rest of the setup is linear or constant. So this equation can be modified to dr, the receiver directivity, multiplied by the effective area of the transmitter, equal to the ratio of the received power divided by transmitted power multiplied by 4 pi r squared. Okay, only the antenna is flipped, but the rest of the setup are the same. Okay, from the previous equation, the equation can be further simplified to this. The ratio between the directivity of the transmitter divided by the effective area of the transmitter is equivalent to the directivity of the receiver multiplied by the effective area of the receiver. So it can show that by increasing the directivity of an antenna, it will increase its effective area, okay, proportionally. And if antenna 1 is isotropic and its effective area can be expressed as ATM equal to ARM divided by D naught R. So if antenna 1, we have the horn antenna 1 just now. So if antenna 1 is isotropic, so the directivity of the isotropic is D naught T, T representing antenna 1 as transmitter, and the directivity equal to 1. And so the maximum effective area can be expressed as ATM is the effective area of the transmitter. The maximum effective area of the transmitter is equal to the maximum effective area of the receiver divided by the isotropic directivity of the receiver. Okay, take note that the maximum area or aperture of an isotropic source, okay, source is the transmitter, is equal to the ratio of the maximum effective area to the maximum directivity of any other source. Okay, let's have an example. Let the other antenna be a very short with L less than a wavelength dipole whose effective area equal to this value, and the maximum directivity D naught are known as 1.5. So we can calculate the effective area of the isotropic source ATM equal to the other source ARM divided by the maximum directivity. So in this case, the ARM or the effective area of the another source is equal to 0.119 lambda squared divided by the maximum directivity. So this is also equal to lambda squared over 4 pi. Okay, so we can also calculate the ARM by using this equation or this relation. So generally, the maximum effective aperture can be calculated by using this equation, okay, considering the maximum directivity. Okay, for further analysis, if there's conduction loss and reflection and polarization losses included in the system, so we need to consider the ECD, the conduction dielectric loss, and also the reflection and polarization. If you still remember, the total efficiency E naught is equal to ER, the radiation refraction mismatch, and ECD is the radiation efficiency or the conduction dielectric losses. So we can calculate the total effective area depending on the condition, whether the additional losses need to be added or not. Alright, so if only the radiation conduction dielectric loss exists. So we consider the ECD in the calculation. And if there's reflection, both the reflection and polarization losses exist in the system, so the total effective area is equal to E naught is the total efficiency multiplied by the D naught. So this is AEM multiplied by the refraction loss and also the polarization loss, power loss factor. Okay, so ER is also equal to 1 minus tau squared. Okay. Okay, let's discuss on the Friis transmission. So Friis transmission equations basically related to the power received, or it is basically the ratio between the power received, and the power received is basically delivered to the load, and Friis transmission is the ratio between the power received to the power of the transmitting antenna. So it is the ratio between power received to the power transmit. Okay, consider a communication system in which you have the transmitter. Okay, you have the transmitter and the receiver separated by distance r, and we assume that there's no additional objects in between, so that there's no absorption or reflection in free space in between the transmitter and the receiver. So in practical, the power density will reduce or will decrease when it radiates in free space. So assuming that this system having no objects nearby, therefore no absorption or reflection happen in between. So the Friis transmission equation is represented as this equation. The ratio between the power received to the power transmit is equal to lambda over 4 pi r squared. R is the distance between the transmitter and the receiver, and the GT and GR is the gain of the transmitting antenna and also the receiving antenna. So if you still remember, the gain equation is basically the efficiency of the antenna multiplied by the directivity of the antenna. So if for maximum gain is equal to the efficiency of the antenna multiplied by the maximum directivity. Okay, so this is the definitions of the Friis transmission, which relates the power received to the power transmitted between two antennas separated by distance r, in which r is larger than 2d squared over lambda in far field region, where d is the largest dimension of the antenna. So the reduction in power density is known as free space loss, and the free space loss factor is given by this equation, lambda over 4 pi r squared. So this is the free space loss factor. Okay, free space loss factor. Okay, next we are going to look at the derivation of the Friis transmission. So this is the derivation of the Friis transmission equation. So we assume that the transmitter, so we have the transmitter and the receiver separated by distance r. So this is the transmitter, and we have the receiver, and they are separated by distance r. Okay, so we assume that the transmitting antenna is isotropic source. So the wave will be radiated equally in all direction. Okay, so assuming that, for example, we have the source as point source in free space. So the input power at the transmitting antenna terminal, represented by PT. So it is assumed as the isotropic source. So the isotropic power density W0 at distance R for the antenna is given by this equation. So this W0 is the isotropic power density, equal to ET is the efficiency of the transmitting antenna or the transmitter, multiplied by its power divided by 4 pi r squared. Okay, so ET is the radiation efficiency of the transmitting antenna. Okay, so for this is for isotropic. For non-isotropic transmitting antenna, so the power density at the transmitting antenna Wt is equal to the power multiplied by gain gain of the transmitting antenna divided by 4 pi r squared in the direction of theta and phi. And this equation can be also simplified to, or can be also represented by ET PT dt divided by 4 pi r squared. Okay, so G, as mentioned earlier, G is basically equal to the efficiency multiplied by the directivity. So for the transmitting antenna, so the GT is equal to ET multiplied by DT. Alright, for receiving antenna, so the effective area of the receiving antenna, AR, is related to its efficiency and directivity. So if you refer back to the previous slide in effective area or with the aperture area, so the aperture area, if you still remember, AEM, the maximum effective area equal to the efficiency multiplied by the directivity and lambda squared over 4 pi. So in this case, for the effective area of the receiving antenna, it is equal to the ER, the receiving efficiency, the directivity multiplied by lambda squared over 4 pi. Therefore, the power collected by the receiving antenna PR is equal to ER/dr in the direction of theta and phi multiplied by lambda squared over 4 pi multiplied by Wt. Okay, Wt is the power density of the from the transmitter. Alright, so since we have defined the Wt just now, so we can replace Wt with this equation. So the equation can be further expanded to this. Alright, so assuming that the transmitter and the receiver are matched, okay, so the reflection efficiency equal to 1 and the polarization efficiency also equal to 1. So this one equal to 1. So therefore the Friis transmission equation can be further reduced to this. Okay, if the reflection efficiency and the polarization efficiency are considered, and so we need to include both the reflection efficiency and polarization efficiency into the equation. So the details equation is as shown. Alright, for reflection and polarization match antenna and align for maximum radiation and reception direction, so the Friis transmission equation is reduced to this. The ratio between the PR over PT is equal to lambda over 4 pi r squared, G naught T G naught R, the maximum gain of the transmitter and the receiver. Okay, so as mentioned earlier, the lambda over 4 pi r squared is known as free space loss factor, which it takes into account the losses due to spherical spreading of the energy via the antenna. Okay, let's look at an example. A typical analog cell phone antenna has a directivity of 3 dBi at its operating frequency of 800 MHz. The cell tower is 1.609 km away and has an antenna with directivity of 6 dBi. Okay, so we have a cell phone here. Okay, so it is the transmitter and has directivity of 3 dBi, so we can say that the dt is 3 dBi, and its operating frequency is 800 MHz, so the F is 800. The cell tower, so you have the cell tower. So this is the receiver. So there's communication between the cell phone and the tower or the base station. So the distance is, so the R is 1.609 kilometer, and the directivity of the receiver is, so the R is equal to 6 dBi. Assuming that the power at the input terminals of the transmitting antenna is 0.6 watt, so the PT equal to 0.6, and the antennas are aligned for maximum radiation and the polarizations are matched. So determine the power delivered. So the question asks you the power delivered, so it's the PR. Assume the two antennas are well matched with negligible losses. Right, so in this case, the first test we have illustrated how the communication system looks like. You have the cell phone as the transmitter and the receiver is the base station or the tower. So all the parameters have been shown in the illustration. So the first thing to solve this is you need the general equation. So obviously the general equation, so from Friis formula, so we know that the ratio between the PR divided by PT is equal to lambda over 4 pi r squared GTGR. Okay, this is the general equation assuming that all the antennas are aligned, well matched, and negligible loss. So we have seen also the G is actually the efficiency multiplied by the directivity. So for both the transmitter and the receiver. So in this case, since the system is well matched and the antennas are aligned, polarization also match, negligible loss, so we can assume that the system is the efficiency is 100%. So it is equal to 1. So in this case, the E equal to 1. So this equation can be simplified as lambda divided by 4 pi r squared, so dt dr. Okay, so the question asks you for PR. So PR equal to that equation. So pt dt dr multiplied by lambda over 4 pi r squared. Okay, so let's go through the all parameters needed. So the pt has been given as 0.6, and then dt, so the transmitter dt is 3 dBi, but all parameters in the equation must be in linear. Okay, you need to use linear values. So you need to convert all the dBs into linear. So in this case, your dt equal to 3 dBi is equal to 10 log of dt in linear. Therefore, your dt equal to, it's around 2 in linear. Okay, so same goes to the dr. So dr equal to, in this case, 6 dBi. So 6 dBi is equal to 10 log 10 of dr. Therefore, your dr equal to 3.9 something, so around 4. Okay, so we have had the pt, dt, and dr. So now the lambda, the wavelength. So wavelength equal to c, the speed of light, divided by the frequency. So it's 3 times 10 to the power of 8 divided by the frequency is 800 megahertz times 6. So the lambda is equal to 0.375 meter. Okay, what else we need? So we have the lambda and the r. The r, the distance between the transmitter and the receiver, is r equal to 1.609 kilometer. So please make sure you use the SI unit of meter. So it's 1.609 times 10 to the power of 3 meter. Okay, so now you have had all the values for the parameters needed. So you need to just include all the values in. So pt is 0.6, dt is 2, and then dr is 4, multiplied by the lambda is 0.375 divided by 4 pi, and the r is 1.609 times 10 to the power of 3. And don't forget the square. Right, so in this case, the PR is equivalent to let's look at the example 2. A dipole, a half wavelength dipole antenna, maximum gain of 1.14 dBi is used to communicate from an old satellite to a low orbiting iridium communication satellite in the L-band, working in the frequency of 1.6 gigahertz. So we have half wavelength dipole. Okay, it's lambda over 2, and the maximum gain, so this is the transmitter. So we have the gain of the transmitter equal to 2.14. Don't forget the unit, and it's used to communicate to a low orbiting iridium satellite. Okay, so the satellite has an antenna with a maximum directivity of 24 dBi. So in this case, you have the satellite with, so this is the receiver, and the directivity, the maximum directivity, so D naught R equal to 24 dBi. orbiting at a distance of 781 kilometer above the Earth. So the distance between the transmitter and the receiver is 781 kilometer. The input power at the input terminals of the transmitting antenna is 1 watt. So the PT is 1 watt. And the antennas are aligned for maximum radiation. Polarization are matched, and assume both antennas are well matched with negligible amount of loss. So find the total power delivered to the receiver, PR. So still you need to calculate the PR. So this is the solution. So you can use, since all the antennas are aligned, well matched, and polarization also match, negligible losses, therefore you can assume all the additional parameters equal to 1. The efficiency, and then the reflection equal to 0, so that's the ER, and the polarization also equal to 1 since the antenna are matched. Alright, so don't forget to convert all parameters into linear values, and make sure you use the SI version, for example the kilometer, and then the linear values for the directivity, and etc. So the final answer is the PR is equivalent to 0.15 picowatt. Right, so with that, thank you.